Hi. Okay, so problems class then, we can get that underway. I have some questions sent through to me, which I'll look at first. If you've got any more questions, then of course put them through on the chat to one side. And speak up if I seem not to have seen the chat. So, okay, one has just come up. Let me do the questions in the order that I received them. So I emailed through was one question was a request that I do a proof by induction on the complexity of terms or formulas. So, I mean, this is apropos exercise 3.6, which was one of the, I mean, I don't know whether 3.6 spurred the question, but if you look in exercise 3.6, that indeed is definitely a proof by induction on the complexity of terms and formulae. I mean, in general, there's also the question about what's the relationship between these kinds of recursions and recursions that we perhaps defined in the set theory course, if you happen to have gone to that course. I suppose just approaching it through the second question first, the second part first. I mean, what we do is we define something by, by a recursion. You define something for more complicated objects in terms of simpler objects. Now, when we do this, when we define recursions over the natural numbers, right? I mean, often people call this induction, right, over the natural numbers. That's slightly incorrect to say that, but it's very common to do that. You prove that something holds for 0, the simpler thing, and then you show how to prove, if you know it for k, you prove it for the next most complicated thing, k plus 1. And then principal induction says, okay, if you've got those two things under your belt, then you know something is true for all n. Right? So this will be a typical, mathematical proof. Definition by recursion and a proof by mathematical induction. So we have the same thing going on with our languages. We want to think of, components of a formula, for example, phi arrows psi. I want to think of, the phi and the psi, these are somehow simpler objects than the compound constructed phi arrow psi with brackets around it. And then that phi arrows psi, that can then be a part of something else. Right? So what you get is the idea that, if you could assume some kind of, you could do this by recursion on numbers if you assign numbers to each of these syntactic objects, terms or formulae. So that number is the complexity. So we look at things, things of complexity 0 are variables, things of complexity 1 are constants. And then if I've got a function symbol and I apply it to a constant alone, then the complexity increases by 1. And so on. So we've got a kind of tiered hierarchy of terms which we've assigned numbers to, which is how complicated they are. And we do the same for formulae. So now if I want to define something, for example, for all terms, I can do that by recursion. I mean, we don't actually have to refer to the numbers too much because we've got the idea that if a function symbol is applied to other function symbols, we want the things it's applied to as being simpler, and they will have been given a smaller number than the function into which they're inserted. So we don't necessarily do the recursion by saying, consider the functions of complexity k. We then define something for functions of complexity k plus 1. What we do is just say, assume it's defined for g1 up to gn. And if n is an n-ary function, then we'll define it for f of g1 up to gn. Well, which has got complexity 1 more than the maximum of the gi's. So we don't refer to the numbers too much when we do definitions by recursion over complexity. We just say, well, as I just did, let's assume we know it for the components of a term, then we'll show how to define it for the term itself. So we're doing the same kind of thing as mathematical recursions over numbers. We're just kind of slightly downplaying the role of the numbers there. But to make it look like, to assure you that it's a kind of bona fide recursion that's going on, we assign this complexity number to the objects. So then, you want to then argue, well, if I've assigned it to all terms of complexity 0, and I've assigned it to defined it for terms of complexity, if I've got it for terms of complexity k, I've got it for the next level of complexity, then we deduce that since every term has got a natural number complexity, we've got it for all natural numbers. And everything I've just said there is fine for formulae as well. So very typical. I mean, I don't want to spend perhaps a lot of time going through this example, but something that one would often see in a logic course is not in my notes because it's kind of almost like too silly an example. But prove that every formula, the number of left brackets equals the number of right brackets. Right, so we've got left brackets and we've got right brackets there in a formula. So, okay, so this is just an exercise in thinking about this, right? I mean, what have we got? What have we got for our formulae, right? I mean, if you look back to how we define formulae, right? So we have atomic formulae. Right, and that is something like, it's a relation applied to some terms, or it can be an equation. So if you want to, so what we've got then is the base case, right? For atomic formulae, number of brackets are the same. Right? And then if phi is a formula, then so is not phi. So you would say something like, by an inductive hypothesis, you assume the number of left brackets here equals the number of rights in phi here. And then you'd say something like, then clearly this holds for not phi. So you've done an inductive step, as it were, where we build the formula not phi from phi, right? So then you'd say that if phi and psi are formulae, and the inductive hypothesis holds for them, then phi as psi is a formula, and trivially it holds for this. So the inductive hypothesis is preserved. Here. And then lastly, if phi is a formula and the inductive hypothesis holds for phi, then it holds trivially for all vk phi. There are no more extra parentheses, brackets there at all. Right? So we deduce then, right, since we've done this here, since every formula is built up in this way, we deduce it holds for all formulae. So in a sense, this is a proof by induction on the complexity of formulae. We've just suppressed the number values of those complexities because it's kind of obvious what we mean. This is more complex than the phi and the psi, and this is more complex than the phi here. So I would say that I would classify this as a proof by complexity of some property of formulae, right? Done inductively here. So I hope that answers that that question. Yeah?
Oh, sorry. Are you saying that you don't need to explicitly quote the complexities then?
Yes, I think I'm saying that. Yes, yeah. This is perfectly good as a proof by induction on the complexity of formulae. We show that something holds for more complex formulae, assuming the inductive hypothesis, it holds for a simpler formula. And I haven't bothered to refer to the numbers. That's all.
Yeah, thanks.
So I think that's fine. And if you look at exercise 3.6, which is one of the questions, that asks you indeed then to prove something by induction on the complexity of here, let's see it. So what you have here is X is either a term or a formula. And we assume that VK isn't one of the free variables. Right? So then show that the subfunction does nothing as defined in the notes. Right? So this is the function that takes this thing, substitutes it for the second thing in the third thing. So we substitute any term at all, t for vk in x. Now, the point is vk is not one of the free variables in x, so this should do nothing. And you're asked to actually prove that it's the case, that it does nothing. So proving it for terms, say, you would suppose that this has been proven for all terms. Now, you could say of a certain complexity k, right? But you could just say, let's assume that it's proven for terms t0 up to tn, and we'll show that it's then Well, this isn't a term, it's a function, right? So you just assume it's proven for T1 up to Tn, and that we've got f is an n-ary function. So then prove it. I mean, what do we want? We're substituting in T for Vk in f of T1 up to Tn. And the inductive hypothesis is, for the simpler terms, we already know sub tvk for each of the ti's just gives me ti. So follow the format of what went on earlier on the top of the page there. Yeah, you don't have to explicitly tell us what the numbers are. Okay, so there's another question. Which I'm not sure entirely what the question was. So did this come from Owen? Is Owen there? Let me just look back. Okay, so the question was about substituting variable symbols for function symbols. As when we define free variables, we end up with a set of variable symbols, but then our definition of substitutable, if we want to check for all Vn psi, we must see if a variable Vk, which may be equal to a function symbol, is a member of the free variables of phi. So see, Owen's not here anyway. Oh, okay, right. I wasn't entirely sure what this question meant, but since there is another question about substitution, we'll talk about that anyway. I mean, I think there was one thing that I would have said perhaps to that is, I mean, we substitute in terms for free variables. When we don't substitute in a term for another term, we don't substitute in a term for a function symbol. Right? You're only substituting in, officially, we're only substituting in terms for free variables. Sorry, for variables, right? That are there in the formula. And of course, you could see the definition by induction here going on, right? We say that T is substitutable for a variable if the formula is atomic, or assuming we know what substitutable is in some simpler formula, we say what it is to be in the whole formula. Likewise, if we know what substitutability for Vk in psi and chi is, and that it holds, So then we know what it means in the more complex formula. And it's only here in this last clause that we have this extra caveat in the definition, right, which says when we can and can't do certain things, or when we are going to declare that something is substitutable or not. And the point of this was to avoid unforeseen or unwanted clashes between this quantifier here and variables that are getting substituted in via the term, perhaps hidden inside this term here. Right? So we're not officially, at least, substituting in, terms for other terms when they're not variables. Right? Although one could perhaps make up a definition like that, and we could perhaps make sense of that. But we're trying to keep it as simple as possible here. So we're only substituting in terms for variables. So I can say more about that, but I can just see there's a question on the chat from Maisie. Let me just try and absorb this. For all vi phi errors psi, does that mean for all vi phi arrows psi? Or, oh, I see. I think I see the question now. For all vi phi arrows psi. Yeah. It goes back to the definition of the recursive definition of what a formula is. So here, notice, right, when we do negation, we put a pair of brackets around. When we do officially, and when we do an implication, we put a pair of brackets around like this. Of course, we leave them out when a lot of the time because they clutter things up, right? But there's always, we don't want to remove brackets and make things ambiguous. But actually here, we don't need brackets, actually. When we're just sort of adopting a convention, which is what the question is about, is that, well, I mean, as the definition goes, we apply the quantifier here to this formula that immediately follows it. So the question was, suppose I write down, for all vi phi arrows psi here. Well, officially, this should have perhaps a pair of brackets around it, right? But this is p arrows q, right? And this is the p, and this is the q. So there's no intention here that this for all has any effect on this psi. As we saw in the definition of a quantified formula, the quantifier applies to the formula that immediately follows it. So in that case, it's this, right? So this is not the same as here. Now we've got a formula and we've quantified it. But of course, the meaning of this can be completely different from this here. Right? Over here, this is saying if phi is true of everything, then psi holds. Over here, this is saying for anything at all, if phi holds of it, then psi holds of it, which is entirely different. Right? So the quantifier here, it just refers to the thing that immediately follows it. And I don't need to put any brackets around, that's just the way we've defined it. Right? So this arrows this is different from, well, I'm repeating myself. That is, this is not the same as this. Okay. Okay, so I'm just seeing if there are any more emails. Okay. Are there any more? Does anybody want to send any questions through to me now on chat? Just wondering what's next best to do for you. What you would like me to do. As I said, these problems classes are for you to suggest what you want done during this time. Normally, I'd probably go over some past homework, but I'm told that there's still some people who've had extensions on the assessed homework, so I probably better not start giving you the answers to those. Can I go through one of the question 3.5 on the exercise sheet? Okay, hope I can. I have to find where that is. If you just give me a moment. Okay, sorry. I have so many clips, different segments of notes. Okay, so let's see. So 3.5 here. So it's asking, right, for which, so you look at the formula over here, and for which occurrences of VI is this function f of V0, V1 substitutable? Right, here. Okay, so I believe this is also part of the homework for next week, so I won't do them all, but I'm happy to do one. So let's try and pick perhaps an awkward one. Okay, let's look at 4 here. So So we have 4v2 relation function v1, v2, v1, and here we have 4v1 s on v3 g of v1, v2 here. Okay, and well, what are we going to substitute? F of v0, v1. So this is v1 here. Okay, so the first part of the question asks you, okay, for which occurrences of v1 is this substitutable? So, okay, so we've got v1 here and here. So you would look up and say, okay, this is an implication. Something is substitutable in an implication if it's substitutable in both halves. Right? So it's incumbent on us to look and see which, if we can substitute this in for here and in here. Over here, it's unproblematic, right? Because this has only got v0 and v1 as free variables. So I can substitute that in here and in here. And there's no clash because this is a for all v2 at the front. And there's no v2 in here. Okay. On the other hand, it's different over here. Here, I'm supposed to be substituting in this thing here for v1. Okay, but then here I've got v1 occurring, right? But actually, right? Okay, here I've not got any, I've just got this quantified v1 in here. So v1 is not a free variable that's over here. So in fact, according to the definition, right, this is substitutable for v1 in here, right? Kind of by the default clause that's there. Right? Sorry. I'm just trying to find a page to justify what I just said. Okay, so the default clause that's down here is saying I've got my function. It will be substitutable for v1, right, in the formula, right? Right. In this case, if phi is for all v1, and this function f that we're substituting in has got v1 in it, right? But we're trying to substitute it for v1, right? So v1 is a free variable of the formula, right? But it's also the case that v1 is not a free variable of phi. So in that case, it's fine. It is substitutable for v1 in phi. Right? So I can substitute this thing in here, right? Because although V1 is one of the free variables of the formula here, V1 is not one of the free variables of this. So it's okay to substitute. This is substitutable for V1 in here, in this kind of default case. So this is substitutable for V1 in here because of the default clauses. Here. This is because f of V0, V1. Okay, this is substitutable for V1 in the underlying formula. So, and although V1 is one of the free variables of this, we have that V1 is not one of the free variables of the whole formula. We call it chi. So it's not, V1 is not one of the free variables of this formula chi. So it's okay. Okay. So it is substitutable. The next part of the question says, okay, perform the substitutions. So you then look back and see, okay, what's the result of doing the substitutions? So you can look back at the subfunction, or look forward actually, the subfunction on page 52. And again, this is a definition by recursion. If I want to substitute a term for a variable in this formula, and it's an implication, I assume that I know how to do it in psi and in chi, and I just put a line between it here and brackets around. So what's going to happen here so I'm trying to get it to focus. So what's going to happen here is I'm going to substitute this in this formula. Well, I'm going to substitute it in this and this, put an arrow between and brackets around. Right? And I substitute this here into here for V1. It does the kind of obvious things. So that's the substitution there into the first part. Now when I come to substitute in the function in the second part over here, right? The result is actually it does nothing. Right? Here's substituting t for vk in for all vn psi. Right? So here I've got this function f substituted in for v1 into this formula that begins for all v1. So actually k equals n, equals 1 in this case. So, and the result is nothing happens. Right? So I'm going to do this arrow here, and nothing is going to happen here. Right? So it's just the same chi again. And then officially to be some more brackets around it. Okay. Any questions there? Okay, and what shall I do now? Okay, I think I've looked at some of that. I've done some of those other exercises on that list there. What type of questions will we have this week? They will be, I think you can already see some of them. I haven't just decided which ones yet. I think you can already see some of them on the edition of the notes that's sitting there at the moment. Let's see if I can share screen here. So we were looking at examples here of theories, theory of groups. I said theory of graphs, deductive closure of this very simple theory, right? A graph is just a set with one relation on it. And okay, so here is, I was going to set 4-2 and probably 4-3 and either 4-4 or something from 4-5. If you look at 4-1 up here, actually that is still, I mean, it's almost could have been in the last section. It's also another proof. Show that one can deduce, I mean, this is like saying if all men are mortal and all mortals are something else, then all men are something else here. So again, this is something that I'm not entirely sure why I put this here. So this is still something that could have been from the last, in the last section. But more relevant to this section is 4-2 to 4-6 here. So, for example, this is exercise 4.6 that's here. Show that the theories of the examples in 4.6 to 4.8 are incomplete. Okay, so let's think about this. I said before that the theory of groups is incomplete. Remember that a theory is incomplete, well, if it's not complete. So to be complete, a theory must, for every sentence sigma, it either must prove sigma or it must prove not sigma. Now, the example we gave is blatantly not true for groups because the sentence that every x and every y, xy equals yx, you know, the multiplication commutes in groups, it's not provable from the axioms. And therefore the axioms are incomplete. And it's not provable from the axioms because the axioms are true in some commutative groups and it's true in some non-commutative groups. So if we could prove the commutativity statement from the axioms, this would contradict the soundness theorem that says that anything that you can prove from axioms, any structure in which the axioms hold, what you've proven holds. So we can't prove the commutativity statement from the group axioms. So the group axioms are incomplete. So what that exercise is, as it were, when you unpack what the exercise is, it says, do this again for some of these other theories, right, here. So think about some property of graphs which some have and others don't, and try and express that using the language of graphs. I mean, it's a very simple, I mean, once you kind of understand what you need to do, it's not so hard, right? I think it's just understanding what it means to answer this question about completeness. So it's training you in use of the word completeness. So just picture in your mind different graphs and just try and find some property that some have and some don't, and write it down in this language. That's the way how you would approach this question here. So again, you can see these exercises, they are, here this is asking you to understand what it means for something to be complete. Here, exercise 4.3. Okay. Can we go over the proof that axiom A4 and or A5 is universally valid if we have time? I'm happy to do this. I see time is almost up, but if you want to stay, we can go over that, or you can look it up later on YouTube. Okay, so let me do one of these. But do leave if you wish to leave. Right. So I'm just trying to find the right page now. Sorry, can you tell me which page are the axioms listed on?
It's 43, I think.
43?
Yeah.
They're in part 1, aren't they? Okay. So ask about A4, A5. You can see that I haven't got these burned into my brain, actually, exactly which axioms have which numbers. Okay, so this then is lemma 349. Okay, so this is axiom A4, this is axiom A5 here. Okay, so this proof was something that we then omitted. Okay, so well, let's do the first one here. So what does it mean? We want this thing here to be universally valid. So this means for any structure and any assignment of variables into that structure, this must come out true under that assignment. Right? Okay, so there's some provisos. I mean, it's only universally valid if this is truly substitutable for VI in phi. Right? We don't want to make a substitution in here and mess things up. Okay, so we'll assume we've got a term and a formula which will have other free variables, and so may the term here. And we want to check that this will always come out true. So you have to just work with the definition right here. So what do? We take an arbitrary structure and an arbitrary valuation here. And what we want to show, and it crosses the line here, is that the valuation makes the formula true in M. So perhaps a comma would be good there. So we've got to show an implication. Well, to show that the implication is true in M, a P implies Q is true in M, it's enough to show that if W makes P true in M, then it'll make Q true in M. And that's what I've written here. W makes the antecedent true in M implies that W makes the consequent true in M. Okay, so we boiled it down to showing this. So we assume this here. Right, so then we may have a little wrinkle in here, right? We're told that T is substitutable for VI in phi, right? But maybe VI is one of the free variables of T. Right? So what we do is we switch it. So let's find a variable that doesn't occur in phi or T anywhere. It's a completely new, fresh variable. And we'll just tweak the assignment, right? So let's suppose the assignment function assigns A when it computes the value of T, the term. Right? So it's this A that we're going to see whether phi is true of A in M. Right? If I substitute T in for VI under this thing here. Okay. So what have we done? We are going to think now the assignment function is going to substitute in, well, what the term is going to be evaluated at anyway, right? A, at the ith place. So this would be the equivalent of substituting in the term for VI and then evaluating the whole thing. Or we evaluate the term first using W, we get A and we substitute that in for VI. which is what's happened here. Now I want to maneuver this, right, so that it looks like this here, which is my conclusion, which is what I want, right? But I have to go through a series of kind of side maneuvers in order to, actually get this to come out. So, and you can see this includes some of the rules of proof that we haven't actually established ourselves, right? But we can appeal to them and see how they might work out. For example, here, I think we're using something about equations. Okay, so let's try and put some sense to it. So if we assume this is the same as this, right? Because k doesn't occur anywhere in phi. So it's not just that it's not one of the free variables. We chose vk so that it didn't occur in phi at all, right? So this is not going to affect the truth of phi in M here. Now, this assignment function assigns a to k, vk, and a to vi. So here I've tweaked the formula. I've replaced in the formula vi by vk. Right? But that doesn't matter under this assignment because it assigns to vk the same thing as it does to vi. So the truth or falsity of phi in M with this tweaked version is the same as this original version. Okay, so this holds if and only if this holds, right? Because now in this formula here, any free variable of vi that's in here has been changed to vk. So vi is no longer a free variable in phi. So this assignment, which worries about what happens at vi, it's not irrelevant now what this assignment does to vi. Right? So I may as well write this here because vi is no longer occurring as a free variable in phi. Now there's a misprint. What is this guy saying here? I think this is T. Yeah, this valuation here gives the value vk a. But this valuation here interprets t also as a. K, remember, is not one of the free variables of t. So this is the same as w of t. So this whole formula then is going to be true in M, just as, well, this will evaluate t as a, if and only if what holds on the line above. Right? And now at last, we can say, well, this assignment is going to evaluate this in the same way as the original w does, because now k is not occurring in any of the variables that's over here. So by that kind of exhausting series of maneuvers, we've kind of massaged this thing here to look like this thing here. So you can see it's a fair bit of work to do something that's kind of reasonably, well, perhaps straightforward if you go through and think about what's going on, right? But it's a little bit tricky, and in the end, it's kind of not so interesting, right? So I'm quite happy to skip these kinds of proofs here. Okay. Right. So let's call that a day then. I'll send an email out later today. I'll try and set homework on Wednesdays, and this will be to be handed in a week tomorrow. Okay, so